pleasure for me. It is a real pleasure for me to have here Professor James Glimm, currently from State University of New York and Brookhaven National Lab. Professor Glimm I don't have to talk about his career, but I will anyway. He made very important contributions in several areas of mathematics, starting from C-star algebras, conservation laws, mathematical physics, and then fluid interface fluid flow, and all sorts of other fields where the interaction between computing and analysis can really play a role. It was also my luck to have him as advisor, and one thing that I learned from him, and that was very important for my life, is that one should keep the eyes high but the feet on the ground. In a more precise term, this was expressed when I was a student as the advice to solve the hardest problem that you can solve, not just the highest that you can think of. So,
well, thank you, Jan. Well, I want to add my birthday wishes to IMPA, and people have already remarked on the extraordinary fact that IMPA discovered 50 years ago the unity of mathematics, or rediscovered, but it was somehow forgotten in the meantime, and only maybe in the last 10 years, 5 years, has this become a mainstream idea in the United States. But we'll catch up. I mean, we actually won a soccer game this morning, and so... So anyway, I thought that appropriate for this birthday, we should speculate about the next 50 years, and maybe IMPA will also teach us 45 years ahead of time what the next 50 years are about. So in that spirit, I thought I should speculate about the great opportunities that mathematics finds itself on the frontier of participating in so many vital areas of science. So maybe the next 50 years will define mathematics as interfaces with computer science, with engineering, with biology, with finance. So I don't know what we've left out, but it seems to me that the opportunities for mathematics to be a full partner in modern science, and even to define the boundaries of modern science more broadly than they've been defined in the past, are so maybe that's what the next 50 years of IMPA will be all about. I will not be here for the next 50th anniversary meeting, I don't believe, but I will look forward to the beginning of that era and as it unfolds. Okay, well, I want to get on with my presentation on fluid mixing. Now, fluid mixing is a little bit related to turbulence in the sense that it involves multiple lengths of activity in fluid dynamics. The wrinkle is that you have two different or multiple fluids, not just one, so that you have all the complications of turbulence, but you have the interchange of two fluids as well. So this is a very complicated subject, and I'm only going to talk about one slice through it, which is the mixing that's generated by acceleration forces. There's been a lot of discussion about the mixing rate. That's the most overall important thing. If you have, say, two fluids and you accelerate them, there's the mixing boundary between them, and the rate of mixing sort of governs everything. And that's characterized by a single number, which you might think would make life simple, but in fact it's generated a lot of controversy because most simulations disagree with most experiments, and so that makes people unhappy. So I will report on how that's actually resolved. There's also some theory which agrees with experiments, and simple mathematical equations which express some of these same ideas. And then we get into the interior of the mixing zone, and then there's equations of the type that Barbara Kiefitz talked about yesterday for solving partial differential equations to describe the structure of the mixing zone, numerical methods, problems in other geometries. Spherical problems are quite interesting because we're interested in things like supernova explosions, and so those are inherently more or less spherical, and other topics depending on what time there is available. So this is a simulation result. This is an early time picture, and this is a late time picture. The color coding is just the vertical axis, so that's to help you understand where you are in the vertical space as you look at this coloring. And the purpose of this plane that's put in here is to demonstrate to ourselves and others that the calculation is still multimodal. What happens as the fluid evolves is the reverse of three-dimensional turbulence, but typical of results in two-dimensional turbulence, which is that there's a passage of information to larger structures, not smaller structures. And I don't know exactly the reason for that, but I presume that's because this problem has a certain two-dimensionality to it. But in any case, it is the case that there's a dominant growth in the structure sizes, so that you get larger structures, and that's important for the continued acceleration of the mixing layer. A structure of a single size will run into a drag phenomena and settle into a terminal velocity and will stop accelerating. So the continued acceleration is dependent on the fact that the structure sizes do grow. So the penetration distance z in this accelerating model or regime then has a t-squared behavior, and it's driven by gravity or some accelerating force. This is a renormalization of the gravity due to buoyancy, the relative buoyancy of the two fluids. So this number is the difference in the densities divided by their sum, and it's a dimensionless gravity term, that a buoyancy term that affects the gravity. And then there's this coefficient out here in front, which modifies everything, and this has to be something less than 1/2. And in fact, it's quite a bit less than 1/2. And these are the range of numbers that it might have, depending on how you go about it. So the experiments themselves have a fairly wide range for this number, but that's nothing compared to the simulations. The theory is also consistent with this number. Now, we have simulations in this range, and so that's good, but many simulations are out of the range, and so that generates quite a lot of discussion. So we tried to figure that out, and we took one of these simulations that disagrees with experiments, and we figured out how to fix it, or at least fix the interpretation of the simulation, and got it back in here. So this is a validation of one approach to why some simulations give the wrong answer. So I'll explain that as we go along. So here is pictures of the simulation, the penetration versus t-squared. The experiments, incidentally, give you a fairly straight line. So the fact that this is curved is already a problem, and I think it is due to the fact that the simulations have early time data. The experiments really belong somewhere over here in a straight line, presumably coming out like that. you can't observe this early time in the experiments, and you can't get to the late time in the simulation. So they're really somewhat different time intervals. These are the comparison simulations. So this is done with no diffusion across the interface, and these are more or less conventional simulations which can't avoid having diffusion across the interface, and so they give a lower growth rate. Now, what happens is that the diffusive simulations have a reduced mixing because the diffusion, the mass diffusion, causes the two fluids to mix with each other, and so that reduces the density contrast, and therefore it reduces the effective density here. So if you have a time-dependent density contrast, which is determined from the simulation, then you can figure out what the effective acceleration should be on the basis of that. If you use this as your time variable, time axis, with the numerically determined density contrast from the simulation, then you see a rough agreement of the simulations. And these give growth rates that are comparable to experiment. So we feel that this is numerically determined diffusion is an explanation for the disparity between these simulations and between many simulations and experiments. This is this dimensionless density ratio, and so it's 0.5, which means that the density was, I guess it's 3 to 1 or something. And for the non-diffusive calculation, that changes only very slightly due to small compressibility effects. But for the diffusive calculation, you can see that it's reduced from that. So the effective gravitational force has been reduced by about a factor of 2, and it's quite time dependent. It has a lot of structure in it. It starts out, because the problem builds slowly, it starts out it's almost completely washed out with the diffusion. And new fluid is entrained into the mixing layer, and that boosts the density contrast back up, but never to its proper level. So these are cross-sectional slices through the two types of calculations. So the cross-sectional slices show just the extremes of the rainbow color bar here. So you have deep blue and bright red, which are the full density contrast. These are the density contrasts here are reduced by about a factor of 50%. So you can see that in that. So we were not satisfied with that and decided to also look further at our analysis. So we did two-dimensional simulations with our what you might think is a fairly modest degree of resolution, 20 cells across this width, and people often do these problems with 200 or 400 cells or more. The reason for picking such a coarse grid, in fact, this is a very fine grid because you want to run this in 3 dimensions, and you want to run it with 10 or 15 or 20 modes. So you want, even if you had this resolution, you'd want 20 times this in 1 dimension, and then you'd multiply by the 2nd dimension. So it becomes quite impossible to even use this resolution. A more typical resolution is 5 cells across this. I didn't even show those results, but you can imagine that has still more problems. So this is the diffusive calculation. And even with 20 cells, which is maybe 2 to 4 times what's typical in a 3D calculation, multi-mode calculation, you can see that the diffusive character reduces the mixing rates quite a bit, and you can see the diffusion here. This is probably the outer limit of what would be reasonable to compute in this untracked mode, but in fact, this is quite a bit more than can really be afforded in these 3-dimensional calculations. That's the 40 cells, which is still further removed from a practical calculation. Now, this we have been using front tracking for quite a few years, and it is conservative in the interior, but not conservative at the interface. So this is just to illustrate that we're developing a new method which is conservative everywhere. The whole issue in making it conservative or making tracking is to describe the geometry of the interface. And to do this, we need a space-time interface as opposed to a space interface. So this two-dimensional spatial interface is a three-dimensional space-time interface. And if you use that, then you can, it's not too hard to make a conservative algorithm that deals with that geometry. Now I want to discuss some theoretical methods for arriving at the same answer. And you might ask why we worry about getting the same answer multiple times. And that's because none of the methods that we're using are really have the character of a rigorous mathematical derivation. So they all have uncertainties associated with them. And so it's desirable to have totally different methods, desirable to have totally different numerical methods, so that if you can get them from the same answer from two completely different methods, then you have a lot more confidence than getting them from one method. So unlike a second proof in mathematics, which contributes maybe 5% to the whole subject, the second calculation in numerical methods contributes a lot more than that. And in addition, we want a theoretical calculation. So these are renormalization group methods, and they're based on statistical physics models of interacting bubbles, and were first proposed in 1960 and have been developed really over the last 10 years and give by now a good, reliable calculation of this mixing rate. So I want to describe the basic principles. The basic principles of these models: you have an ensemble of interacting bubbles, and each one has a motion of, say, if you had an infinite array of identical bubbles, so a periodic array, and this problem can be solved analytically using potential theory, at least in some approximation. So this is a reasonably well-defined number. It can also be calculated, and it also can be measured experimentally. So we believe we know this number as a sort of a hard fact. Now then you want to get the interaction of bubbles which are not identical, but are at different elevations relative to each other. And so we use a superposition law to regard the bubbles that are separated like this. We think of this as being a superposition where you have a bubble on a larger length scale combined with the bubbles on the small length scale, and you add the velocities. And then you need a bubble. So this is the second input to the model, is the superposition law. And then you need a bubble merger to remove small bubbles and expand the ones that survive in size. As I mentioned in the beginning, the whole phenomena of acceleration is due to the increase in size of all the structures. So this would give you a fixed velocity, and this is what gives you a fixed acceleration. So you need these three components, and then you can get a fixed acceleration, which is what Sharp and Wheeler did. And if you use the superposition law, you actually get the right answer also, which is what this alpha is up here. And so if you solve this, you get a renormalization group. If you solve the statistical model, you get a renormalization group equation, and the fixed point gives you the alpha. I think I will skip over some of the details of that. And go into the next topic, which is the relation of the heavy fluid mixing rates to the light fluid mixing rates. And so we look at the center of mass, and that should also have this acceleration law. And for some reason, which we don't fully understand, this acceleration is approximately 0 unless you get up to with numbers very near 1. So if you forget about all this fancy stuff and just say A equals 0, that will cover most fluids. And this introduces a constraint between the heavy fluid mixing and the light fluid mixing. And so that means that the theoretical model that tells you about the light fluid mixing, together with this thing being 0, will tell you about the heavy fluid mixing. And this ratio is actually a solution of a quadratic equation. So we have derived that equation and found that solution, so we can completely predict the heavy fluid mixing, can predict the light fluid mixing theoretically. You can also predict the heavy fluid mixing theoretically. And remarkably, that happens to agree very nicely with experiment. And so here's some experimental data points, and these are the curves. This curve at this end, there's actually 3 curves at this end, depending on this gamma. This exponent is rather loosely determined. The endpoint is fixed by free fall, so you have to go through here for the heavy fluid side. And there's just a little bit of spread in how the curve might be here, but you can see that it fits the data very nicely. So that's a very nice theoretical prediction. Then we want an equation for the mixing zone edge. We have this growth rate, and so that gives the long time asymptotics. There's an equation. This is basically, you can think of this as Newton's law, because this is an acceleration term. This is force due to buoyancy, and this is force due to drag. So this is a phenomenological term, and you have to worry about what this coefficient is. This is given directly from physics. And this is Newton's acceleration term. This is an added mass. What it's saying is that if the bubble is rising in the heavy fluid and it accelerates, it has to accelerate not only itself, but it has to accelerate some heavy fluid and push the heavy fluid out of the way so the light fluid can go ahead and expand. So this added mass is well known in fluid dynamics, and the conventional value is you want to take k equals 1. So this equation has one undetermined parameter in it. And so you can solve that, and the long-term asymptotes you know because you know what these alphas are, and so that fixes the C's are fixed in order to agree with the long-term asymptotes. So this is now completely fixed, and instead of predicting the long-term behavior of the mixing, we can determine also the mixing behavior for all time scales as long as it's in a chaotic regime, so the equation's applicable. So now we have a prediction of the mixing zone edges for all time, at least once it starts being chaotic. Now these equations have been studied by many authors, and there's a little bit of carping about how it took a while to get the thing formulated in a nice way, which I want to skip over. This gives you the relation between the drag coefficient and the mixing rate, just given by these simple formulas, and the asymptotics, then the leading order asymptotics in terms of this number A, which is related to alpha and C. So there's only one parameter, and that parameter has been determined theoretically. And for the, so this is for steady acceleration. For shock acceleration, as a freebie, you get a second series of experiments, and they also, now there's 0 parameters for this experiment, because you've already fixed the parameters from the steady acceleration. In the shock acceleration, you get an analytic solution for all time, and there's no parameters at all, because this number here is already determined up here. And what you get is growth rates with a theta, an exponent, and that exponent is predicted. So this gives you these drag coefficients as a function of the density. I didn't mean to do that. I think I have gotten to the wrong point here. Okay, I pressed the wrong button, that's all. All right, so now we want to discuss the equations that describe the interior of the mixing zone. So up till now we have looked at the motion of these edges. So this thing has a height z equals alpha a g t squared, and now we want to look at the interior of the mixing zone. So there are many ways to model this, and there are many different flow regimes. Multi-phase flow is characterized by a large number of different regimes, and the region that we're taking to study is the region in which there's fairly large coherent structures. So we're thinking, if you remember the original picture, it sort of looked like this. So we're averaging these fairly large structures, and we call that a chunk mix regime. And so we want to keep complete fluid variables for each fluid. This gives you mathematically stable equations. There's some controversies over equations and Hadamard instability. It also gives improved physics for the mix because we get, a larger set of equations. We can include pressure differences. And the thermodynamics is treated on a process-independent manner. We have a new closure for this regime, which has actually 0 parameters. Remarkably, there's an analytic solution for the incompressible case. This is in 1 dimension, and for the solution asymptotics in the weakly compressible limit. So the entire theory in this regime, weakly compressible and incompressible, is totally solved in closed form. So let me just say a little bit about closure. This applies to any set of averaged equations for anything. So you start with some equation, you want to average, so you put a bar over everything. And the trouble with that is that you get, with nonlinear terms, you get undefined quantities like this f of u with a bar on top, where you really wanted f of u with a bar on the u, and it's nonlinear, so you can't do that. So we introduce a new f, which we call f renormalized. F renormalized of u bar is equal to the bar of f of u, and so now we're happy we've solved the closure problem. Of course, we only solved it by introducing something over here that we don't know what it is. So you actually have to go back and figure out what f renormalized is. And this is where the major difficulty of all averaging occurs. And much of science is really concentrated at trying to find some reasonable f renormalized. And people talk about multi-scale science, and this is really where it comes about. This is where you can go from the microphysics to the macrophysics. And to do that, you have to average, and to do the averaging, you have to find the f renormalized. So this is the essence of the problem of multi-scale science. And so just to illustrate, the simplest equation is for the volume fractions, which is the average of the characteristic function averaged over some ensemble. And if you write out the equation for the transport of that, it looks like this. And this is this undefined quantity, which we want it to look like this. So what you do is you just define V star to make this an identity, and that says that V star is a ratio of this quantity, you don't know what it is, by this quantity, the grad of the volume fraction. And so now you have a definition for V star. And again, you haven't done anything because this is mathematics. The ultimate issue about ensemble averages and closure is that it isn't mathematics, it's physics. I mean, unless you want to get into some horrendous problem in calculating probabilities of ensemble averages. But short of that, in any realistic sense, it is a problem in physics, and you need an expression for V star that replaces this identity, which is somewhat useless because you don't know what either side of the identity is. Now, it turns out, and this isn't usually the case, in this kind of business, there's a theorem, and the theorem says that V is a convex combination of these of the velocities of the two phases. And that comes about fundamentally because there's a few constraints in this problem, and there are only a few variables. There happen to be enough constraints. So one of them is scale invariance, and the other is Galilean invariance. And when you get through with that, you're just stuck with this theorem, and that's nice. What we did was we still had to find these coefficients, and we started out assuming they were linear in the volume fraction, and that turned out to be wrong. And then we assumed they were fractional linear, and that turned out to be a very lucky guess because there's another theorem which says that they have to be a volume fraction, which we didn't know at the time, but found since then. So these mixing coefficients, these have to be of the form of a fractional linear. I've left out some terms. Some of the terms you can fix because you have boundary data, and it has to equal a certain value at the top and the bottom. And so the only undetermined parameter is this coefficient, and so that's what I'd call a constitutive law, that coefficient, and then you can actually determine in the incompressible case that it's a ratio of edge velocities. And apparently this is a convenient choice for the same equation for the pressure has the same form, and so we want to make that choice probably. And then you have to get the edge motions because they come into the equations, and so the edge motions come from the buoyancy drag equation that we just discussed. Now here's this theorem, and it turns out that there's an exact identity, and it is fractional linear, and you can have a formula for the for this constitutive law, and it equals this. Now, in a way, that's a step backwards because the equations, there aren't enough equations, and if you derive an equation for something that you thought you didn't know, then you're stuck because it isn't new, it's actually old, and it's so we don't actually want this, but it suggests what we do want. So this is an identity, and it is enforced by the original equations. And so what we want is no length scales interior to the mixing zone. So this should be given as a number and not as a function of space or time of space. So we say that it has to equal the integral average of that other quantity over the mixing zone. And so since I want to challenge this as a mathematics audience, what have we done to our equations at this point? I don't actually know, but apparently the equations are no longer hyperbolic because one of the terms in them is given by this integral identity as a term in the equation. So somehow this integral identity has crept into the equations. So what have we actually done to the equations? Well, I don't have the answer, but if anyone can figure that out, I'd be glad to get the answer. In any case, we can get an analytic solution, and everything is known explicitly. This is just to illustrate. I think these formulas are a little hard to grasp, but my main point is simply that we know what they are. And the only thing that's a little tricky is the pressure. The pressure has a mean pressure, which is and a pressure difference, and they're both given by ODEs. And it turns out that this is also integrable in closed form. That actually needs Maple or something like that to do the integrals. These are continued fraction integrations. But you can do that, and the answer is a little bit depressing. It goes on for about 3 or 4 pages. But it can be understood and reduced to half a page, which I won't do. Now, I want to give you these solutions. Everything looks very boring except for the pressure differences. So most of the physics is actually in the pressure difference. And the other parts of the physics are all more or less straight lines. And so, in fact, I don't think that we'll get very far with distinguishing between one model and another on the basis of data, because straight line data will probably fit most models reasonably well. Now, here's where there is some real physics entering, and this is the pressure difference. The pressure difference, which is the pressure between here and here, between the tip of a bubble or a spike, and the region in between, this is exactly what gives rise to the drag forces. And the drag forces are these phenomenological things that we understood only because we could relate them to growth rates. So it would be nice to understand these at the level of physics, these drag forces and the pressure differences. So here in the compressible case, where we don't know the alphas and we don't know, therefore, the drag coefficients, we experimented with a lot of different drag coefficients in a compressible case, and we looked at the pressure differences as a function of that. And you can see that these pressure differences are sensitive to the change in the drag coefficients. Nothing else is sensitive. Everything else in the model totally ignores the fact that we don't know the compressible drag coefficients when solved compressibly. So all the physics really sits in these pressure differences, and this is exactly what's left out of most of these multi-phase models. So they have parameters in them, but without as much of a, I think they've left out the important physical basis for the parameters. So this is an example of something that isn't sensitive, and this is showing convergence to the incompressible limit. And as you can see, these are different values of a number that's more or less a Mach number squared. You can see that from the moderately compressible to the highly incompressible, there's barely a difference in the volume fraction. And you can see the volume fraction is also fairly nearly a linear function of the distance through the mixing zone. And so it's for that reason that experimental data isn't going to go a long way or micro-physical simulation data of the full problem without averaging isn't going to go a long way in separating these models or validating them. Because I think that pretty much everything will agree. Here we're back to the pressure differences, and you can see the convergence to the incompressible limit has quite a lot of structure in it. This is convergence of the pressure difference under mesh refinement. So under the coarsest grid, you can see that it's a little bit off, and after that it settles down. All the other variables converge very rapidly. So it's only the pressure difference that has any sign of life in it. For example, this is the light fluid velocity, and you can see just the smallest difference as you change the mesh. Incidentally, this mesh allows, the coarsest mesh here allows, I think, around 20 cells in the mixing zone. It's customary, I would look at these mixing zones as hydrodynamic waves. So it's much more complicated than a shock wave, and you might think of it, for instance, as a reaction front. It's some region in the flow where you have single phase on the two edges and this mixing zone in the middle. So I would think of it as a kind of a wave structure that separates the two single phase regions. And so it's desirable from the point of view of numerics. People are proud at how few cells they can get in the mixing zone instead of how many. And so a good shock wave algorithm has only 2 cells or so inside the shock wave. And so from that point of view, having 20 is quite a lot, but it's typical of what a reasonably well-resolved flame front would have. And so it isn't desirable to have hundreds of cells inside this mixing zone. In the end, the mixing zone might be a small part of a much bigger problem. And if you have hundreds of cells in the mixing zone, then you're going to have trouble with the bigger problem. So the fact that it converges with 20 cells is not too bad. Now I want to switch gears again. This is comparison to laboratory experiments, and this is our simulation code, and these are the experimental results. We're on target. An initial comparison with another code was off. This was later fixed, so you should think of this blue line as actually going through the data also. And this is the spherical calculations, again, with mesh refinement, and these are the mixing rates. So there's an inner and outer edge, and this is the distance between the inner and outer edge of the mixing zone. and they are convergent under mesh refinement. So this is the typical simulation in the spherical problem, and this would happen during a supernova collapse, for example. These are regular perturbations. There's actually sine waves, but we get the same thing with spherical harmonics. And we originally thought that there was an error in this calculation because of the lack of rotational symmetry in the picture. Now, actually, the physics doesn't have a rotational symmetry because the picture has an axis of revolution here. And if you rotate, you're going to rotate that axis of revolution. So the problem is not spherically symmetric once it's been perturbed. And so after repeated urging of the postdoc who was working on this to fix his calculation, he finally fixed my understanding instead. And we managed to prove that this is actually in the physics and not in the numerics, and so that belongs there. And then we went on to do the random case. But this is an example, you see, where you want to understand what you're doing first, because otherwise you could confuse anomalous effects up here as having some numerical aspect, whereas in fact they are really more of a physics aspect. And so if you want to do statistics, it's probably better to look in the equator region and not look in the North Pole region. Now, these problems have too many variables, and following work of my colleague, former colleague Chang Zhang, we introduced a scaling in the strong shock scaling limit and got rid of one variable. And so this is the same, similar problems, but done with a shock wave, initial shock wave Mach numbers of 10, 20, 50, 100, 200, and 300. And with appropriate scaling, everything lies on the same curve. So there's no physical principle that I know of that says that this limit has to exist. And so again, I want to challenge the mathematicians to find a derivation of why this should be the case. But it's evidently asymptotically correct, and furthermore, it kicks in at a fairly reasonable small number of m, so it's a very nice limit. It'd be nice to have a theoretical explanation for that. Here are some growth rates of the inner and outer edges, and this is in the different sectors. So this is the equator and the mid-latitudes and the North Pole, which you can see behaves differently, and the inner edge and the outer edge. Here is one of these. It isn't quite a straight line. This structure is due to the mushroom cap bubble and spikes. But I think if there was more randomness and more multi-mode behavior, this would go away. And this is what we had predicted to be more or less a straight line in our models. Here is another one of these spherical problems. This is the supernova explosion with the heavy fluid driving the light fluid. So these are heavy elements, and this is the hydrogen on the outside edge. And it gets to be fairly complicated. Now there's by now fairly good data on the supernova that you can't resolve and see pictures like this from even the Hubble telescope. But what you can do is you can get the timing of the release of different isotopes. And so the isotopes are originally stratified by their density, and so that, for instance, carbon is fairly into the interior, and helium and hydrogen are on the outside. So you look for when do you start seeing carbon coming out at the surface, and you can get the time history of the degree of mixing from that. Now, when you do that, you can get an estimate of the mixing rates, and then you can do the simulations of the mixing rates. And just as there's a factor of 2 difference in the mixing rates between laboratory experiments and simulations, there's also a factor of 2, more or less, difference in the astrophysics mixing rates and the simulations. Now, there's a theory that the experiments have been contaminated with noise, and the noise has caused this linear alpha to more or less double from what it would be in idealized. And I don't want to get into that too much, but all I'm saying is that the people that invent these theories about why simulations are different from simulations have a challenge to them, because there are more and more experiments that are totally different that also disagree with simulation. So that the people that can explain why the simulation, the experiment should be different, have to explain not only two different, very unrelated types of laboratory experiments, they also have to explain the astrophysics as well. To date, they haven't done that. So at the moment, that just looks like a discrepancy between simulation and experiment. So we're planning to do this with our own calculations. We have gotten the right values for the laboratory experiments. We'll see whether we get the right values for the astrophysics problem. This is, I won't show you this, but we're doing the flow of diesel. This is diesel fuel coming out of a jet, and these are phase transitions in the diesel fuel where it's gone into vapor phase and so on. Then I have the summary, and then I want to show you a short movie. So we have planar results, consistent theory, simulation, and experiment. We have a chunk mixed averaged model, mathematically stable and thermodynamically determinate. We have numerical analysis, code comparison. We have new algorithms, new numerical algorithms, spherical results, various types. Let me show you the movie. And the movie's on a completely different topic. This is the target design for a new particle accelerator. This design of a muon collider to make muons and run them into each other. Muons are super heavy electrons, so you get a lot more energy, and so you make an interesting collision. So this is a proposed accelerator. And you generate the muons by putting protons into a target. And so the target is a jet of mercury, and we want to load up this jet of mercury with protons, and then we want to see what happens. So this part of it is a purely hydrodynamic issue. And to emphasize the importance of these calculations for target design, I can tell you that there is a similar machine used to make neutrons, a neutron spallation neutron source. And the target in that case is not a jet, but a jar of mercury. And you shoot protons into the jar of mercury and generate neutrons. And that target is failing, and this machine is therefore in jeopardy. And the machine, I don't remember the budget numbers because they don't stick in my head, but there's some fraction of $1 billion. Typical large accelerator is more than 100 million and probably less than $1 billion, something in that range. So when you misdesign something of that type, it tends to get people's attention. Now they may still redesign the target and make it work so that it isn't, I'm not saying the machine's a failure, but I'm saying that numerical simulations of the hydrodynamic part of something that's fundamentally something quite else can still be quite an important issue. So let me show you this, and you'll see the instabilities as the jet of, as the protons are deposited. There's the protons coming in, and it gets hot, and it expands, and it goes back and forth, and it doesn't look like it's doing much, but just wait. Okay, so that's the answer. Well, there were two theories as to what would happen. And one of them was this, that you get this complicated structure and a lot of spray and eventually droplets coming out. And the other theory is that nothing much would happen. So That's what life is like in the fast lane, and one of the theories was wrong and the other one was right. Now what's going on here is, from a point of view of hydrodynamics, you put in a lot of energy and it gets very hot, and that generates a classic shock tube Riemann problem. And so you get a shock wave going out here into vacuum or air or whatever it is, and a rarefaction wave coming back into the mercury. And that rarefaction wave will come through and hit the other side, and at this point it will reflect, and when it reflects, there's a light fluid on the outside, so it reflects as a shock wave, and the shock wave comes back, or a compression wave comes back and hits the interface, and I guess at that point it goes unstable. So it's on the second bounce, it goes unstable, and this is what's called a Rickmeyer-Meshkov instability, a shock wave hitting an interface, and that's unstable no matter which way the density contrast goes. And so it goes unstable probably starting at the second bounce. The initial perturbations are very small, and so I can't actually say by visual inspection when it starts going unstable, but I will run that again, and so you can see that for yourself with that explanation, that the instabilities grow very slowly and apparently don't grow from the beginning. So here's the energy deposition. Still looks pretty stable. That's the second bounce. Okay, and now that looks like it's unstable in the second bounce, and then it just keeps going unstable. Well, we haven't analyzed this experiment extensively. This is just a calculation, but we have the apparatus. All of the material that was developed in this talk, most of it's in planar geometry, but it could be put in cylindrical geometries. And so we could analyze this and see to what extent, whether it's the second bounce or what it is that's causing this instability. We also want to take this to a later time where you get, these would break up into spray then. So that's just a surprising application. There are many illustrate that whatever you think of as a list of multi-phase flow applications, there's always another one. So now we can add target design for proposed accelerators to multi-phase flow applications. So I think I'll stop on that note. Thank you. Yes.
This model is applied for prediction of water pollution, for instance.
Water pollution. No, we don't use this for water pollution.
Oil and water, for instance, the spread of oil in the ocean.
I am working on problems like that, but this multi-phase flow is different. There's many multi-phase flow theories, and the oil and water is a different multi-phase flow theory. Darcy's law and Buckley-Leverett equation are averaged equations, but they're different from these. This is the problem without the rock, just the two fluids.